In this video, we continue the discussion on Haar measures for locally compact groups, and we are going to prove the existence and uniqueness of these measures. Okay, so let's start about the existence. So let's recall some notation. So we have that G is a topological group. Eventually, is going to assume G is going to be, we assume that G is locally compact. And then we consider the positive continuous function with compact support. So non-negative and non-constantly zero continuous compactly supported functions on G. Okay, and then what we did is for any f and phi in such a space, we defined this number, so how much f is covered by translation, the translation of phi, which is the infimum of all the sum of cj's, j from 1 to n, where n is a natural number, cj's are positive numbers, and f is less than the sum of cj's phi precomposed with the left translations by numbers xj's in G. Okay, and then we defined this operator I of phi, that is f respect to phi, divided by f0 respect to phi after having fixed some f0. Okay, so this is an approximation of our left invariant operator. We are looking for a left invariant linear operator on this space, such a way that then Ritz representation will give us a measure. Okay, so we have proved some properties about these quantities. In particular, we have the following. So we have that by construction, the operator is left invariant, namely if phi of f composed a left translation is equal to if phi of f. And okay, we should pay attention, we should not call it operator because this is it is not a linear operator, but in general we have that is subadditive. This we proved in the previous video. F1 plus F2 is less or equal than I of F1 plus I of F2. And moreover, we have another property we should discuss now, that if F0 is the function that we use to normalize, we have this bound, upper bound and lower bound for this operator I of phi. So here is F0 respect to F and is F respect to F0. So let's prove this function here. Let's give a number here. Let's call it, denoted with this symbol triangle. Okay, so regarding this formula. So recall that we proved there is this composition. If you have three functions, we have this bound G, which just come from composing functions. Okay, we have proved this. So if you take phi of f, so which by definition was f respect to phi and f0 respect to phi. Now let's use this bound on the numerator, and we have f respect to f0 times f0 respect to phi divided by f0 respect to phi, which is f respect to so this simplified with this and f0, which is the first bound in this formula. Now regarding the other bound, what we have, and if you take this quantity, so let's multiply above and below about f respect to phi, so f0 respect to f respect to f respect to phi. Now let's use again this bound for the denominator, and what we get is f respect to phi divided by f0 respect to phi, which is exactly I phi of f. Okay, so, and therefore we proved this equation here, which we're going to use it, I think, twice. Okay, let's continue. So we have this operator I of phi, and let's pay attention because it's sublinear, but it's not linear. Okay, so what should be the idea? The idea that is, as phi is supported in a smaller and smaller neighborhood of the identity, then as close to a linear behavior we have for f, for I, for the operator. Okay, so I'll write the idea. The idea is that as the support of phi converge to the unit element singleton I, the operator I of phi will converge to okay, left invariant. This is clear because it's just going to be a limit of left invariant operator, left invariant, but it will be continuous, linear, positive operator, and giving us a left invariant Haar measure by Ritz representation theorem. Okay, let's now state exactly what it means that as the support gets closer and closer, the limit gets closer and closer to be linear. The operator gets closer and closer to be linear. So this is the last lemma we need to prove before proving the existence. Okay, so for any two functions, f1 and f2, positive, continuously supported, and for any epsilon, there exists V, an open neighborhood of the identity element, so open, such that if the support of phi is contained in this neighborhood, then we have linearity up to an error of epsilon. So we have this extra epsilon. If we didn't have this epsilon, because we already also have the other inequality, then we would have the other inequality would have linearity. Okay, so this is the lemma that we want to prove. Okay, so proof. Let's fix psi. With so we want psi is 1 on the support of f1 plus f2. So this is these are compactly supported. So this element, this set is compact. So we could by horizon, we can find a function that is 1 on the support and then decays continuously and is 0 outside another compact set. Okay. Then what we do next, we also fix delta. Actually, this delta we need to be has to be chosen carefully, but I will tell at the end how to choose it. So this will be determined. It's going to be will be determined only based on f1 and f2. Okay. Now, okay, let's consider h to be the sum of the two functions plus delta times phi. Okay, and hi is going to be the function fi over h, which should be understood that is 0 outside of support of fi. So this is compactly supported, this is continuous on the support, and then it's going to be 0 outside. And then what should be clear is that this function hi's are continuous and positive and compactly supported. Okay, all of this is for all I equal 1 or 2. Okay, now since exactly hi's, each of these hi is continuous and compactly supported, then one could see that because left translations are continuous maps, one could prove that not only these functions being continuous on a compact and non-zero on a compact set, they are uniformly continuous, but they are uniformly with respect to also left translation, right? What I mean is there exists V, open neighborhood of the identity, such that if we move, if the increment, let's write here that this the increment is in V, then hix, hiy is less than delta. So this is uniform continuity. See, if you take 2 points that differ, and this is exactly how they differ, right? So in fact, if you take y, what is the number that you have to multiply on the right of y to get x is exactly this number here. So if you move it by this quantity small, then you get a small change of the value of the function. This is exactly uniform continuity. Okay, so this will be our V. Now let's also take function phi positive, compactly supported, with support of phi in V. Okay, so now let's give a bound. So let C1, Cn, 0, yes, okay, such that H is bounded by this sum of Cj phi Lx j, let's put -1 here. Okay, so this means that this sum is a bound for the number h with respect to phi. Okay. And now let's observe that if we have, but it's the uniform continuity, if this product is in the support of phi, since phi has support inside V, then this number is inside V, and therefore we have this property, right? Which means that this implies that we have hi x minus hi xj. This is less than delta. Let's give a number to this equation, star. Suppose we have, okay, then we have this bound. Let's bound now the number f respect to phi. So we can bound like this. Fi x. Okay, now this by the definition of G, this is h of x times hi of x. And now these are all positive numbers, and I bound, so I have the bound for h, so this is Cj phi of x xj minus 1 hi x. Okay, then we use the equation star. So this is sum j from 1 to n of Cj phi x xj minus 1. Now instead of hi, I put hi of xj plus delta. And of course I can write this as sum of Cj phi x xj minus 1. No, I'll put that at the end. No, let's just write it like this, xi xj plus delta. Now these are numbers, times phi x xj minus 1. So now you see that these are numbers depending on the index j, but they're not depending on the variable x, which means that therefore we have a bound for the number fi with respect to phi. It's going to be less than sum of xj hi xj plus delta. Okay, we have this bound. Now let's sum this quantity for I equal to 1 and 2. So we have f1 respect to phi plus f2 respect to phi. Just apply the previous bound. So sum j, Cj is going to be h1x plus delta, and I put just in one parenthesis h2x plus delta. Now let's use the fact that here that h1 plus h2 is less than 1, and we get that so why h1 plus h2 is less than 1? Let's remember what this h. See, if we sum them here, we have f1 plus f2 divided by h. But see, h has this extra piece, so the ratio is less than 1. Okay, less than 1. So we have that this is less than sum of Cj 1 plus 2 delta. Okay, good. So this is a bound. And let's remember that, okay, so of course this is, we can write it as 1 plus 2 delta sum Cj. And this was an arbitrary bound for h with respect to phi, right? So taking the infimum, what we get that f1 plus phi plus f2 plus, plus respect to, respect to phi is bounded by 1 plus 2 delta h with respect to phi. Okay, so now let's divide by f0 respect to phi. And what we get the operator, maybe I write what to, so divide by f0 respect to phi, and what we get is the operator on f1 plus the operator on f2 is less or equal 1 plus 2 delta the operator on h. Now, by definition of this inequality, by definition of h, this is 1 plus 2 delta I phi of f1 plus f2 plus delta psi. And now let's use the I is subadditive. So here we have subadditive. And we get, here we have 1 plus 2 delta I phi of f1 plus f2 plus delta. It's also constant get out, we showed last time, not f, but h. Not h, psi. Good. Okay, now we can conclude, right? So we want to, so this object here, it's, see, there is this term, that is what we want to bound. So we want to have it. So what we're asking, if this is less on I phi of f1 plus f2 plus epsilon, right? So here we have this term, times 1, and the rest we have to make it infinitesimal. So we can conclude if we can choose delta, so that what was left, so it's phi f1 plus f2 plus 1 plus 2 delta I phi psi, this is less than epsilon. Okay, can we choose this? Now, by the equation, the triangle equation, which was it? Was this one here. Now we're going to use this. Okay. What we have, so by this, v above left hand side is less or equal than, okay, 2 delta. Instead of I phi, I can put f1 plus f2 respect to f0 plus 1 plus 2 delta psi respect to f0. And now we have to understand that this is a value that fix f1, f2, and f0, of course, and psi. This goes to 0 when delta goes to 0. So which is a value independent on phi that goes to 0 as delta goes to 0. And this concludes the proof of the lemma. Now we prove the theorem. We are now ready to prove the existence of Haar measures on locally compact groups. So we are going to prove that for every locally compact topological group, let's call it G, there exists a left Haar measure on G. Okay, let's prove it. So we fix some F0 and see compactly supported positive function continuous. And for every F, for the other F, we consider the interval xf to be F0 respect to F inverse, F respect to F0 is a subset of R. And we let X to be the infinite product of all these intervals. So this object here is an infinite product of compact intervals with the product topology. Okay, what is the idea? The idea is that instead of looking for a measure, we are looking for an operator on continuous compactly supported functions, and we define some operator that are almost linear that for any f they take value inside this interval. Okay, so it means that as a function on f belongs to this infinite product. Now each of this interval is compact, and now Tikhonov theorem tells us that with the product topology here, this space is compact. Okay, so, and we are going to take more or less like a limit of these operators I phi when phi tends to have smaller and smaller support. So Tikhonov theorem implies that X is a compact space and is also actually Hausdorff. Okay. Now, what we have is that our operator I phi assigned to any f an element inside the interval xf. This is for all f in C plus C, right? And this was the equation that before we called it delta. Okay. Now, then for any phi, I phi can be seen as a point in the space X, this infinite product. Okay, now for all V subset of G, we should think of compact neighborhood of the identity, we will consider the set KV to be the closure inside X of all the points the operators phi such that the support of phi is inside this operator v. We're taking this set and taking the closure within X. Okay. So now let C be the collection of all the compact neighborhood of the identity element in G. And this collection, okay, which is not empty, exactly because we assumed that G is assumed locally compact. Okay, here we are using that G is assumed locally compact. So this family is non-empty. Okay. So now we're going to see, like, for any element in this, for every V inside this family here, we are going to consider this set, which are going to be closed sets in a compact set. And now we are going to see that they have finite intersections is still non-empty. And then we are going to take a point that is in the intersection of all of them. So I make you notice that for all V1, Vn in the family C, in the collection C, if we intersect these sets, then for sure we are going to have the families of all operators whose support is in V1 intersect Vk, Vn. Now, what's important is that this object here is still a compact neighborhood of the identity, right? So you can always find a phi that has support inside here is non-zero. So which means that this set is non-empty. Okay, so this means that when we are looking at this family, when V varies, finally many of them have non-empty intersection, and therefore since we are in a compact space, the intersection of all of it will be non-empty. So I will remind you this fact. Recall that in a compact space, every family of closed sets for which every finite intersection of finitely many elements of this family is non-empty, has non-empty intersection. Hence, what I'm saying is that in particular, there exists a point in the intersection of all the k of V when V varies in the whole family C. Okay, so we can take an element in this intersection. Okay, let's call it I, and let's show that I is the operator that we were looking for. It's one of the operators we were looking for. Okay, so what does it mean that V is in the intersection of all of them? It means that for all neighborhoods U of I in X, U intersect with all the elements for which the support of phi is contained in V. This is non-empty for all V in C. Okay, and in particular, for all epsilon greater than 0, and for all v in C, we can take neighborhoods of the family f1, fn in C plus, and we can always find a phi such that the support of this phi is inside this V, and E on every of these F differ from I phi by less than epsilon. Okay, let's give a symbol, this symbol here to this equation. Okay, very good. Okay, so let's check. See that this is see, it means it's very close to one of the operators that we want. Now, since this is almost linear, we will prove that this is almost linear, but for all epsilon, and therefore it's linear. So let's check that I is linear. Okay, so we fix epsilon, and we fix f1 and f2 positive continuous compactly supported function, and then we take the v. Okay, let's take the v as in the lemma. No? Now we look at the lemma that we proved. Right. Now we apply with this f and this epsilon, we have this v. Okay, for which we're going to take support of phi inside this v to obtain this almost linear behavior, right? So let's take v as in this lemma. So take v from lemma above. Okay, and then we take phi as above, I mean here, and we take the phi for such a v, okay, to have this property here as above in this equation here. For which functions? For the function f1, f2, maybe we should also take f1 plus f2. Okay, these were the functions that we are considering here. Okay, then what do we have? That I of f1 plus f2, okay, this is definitely smaller than I of f1 plus I of f2, since I is the limit of such I phi's which are linear, which are sublinear. Right. So we are getting this for every phi, I phi, so we will get it for I as well. So the difficult part is the next one, and this is the important part. So I f1 plus I f2. Let's see how it differs from I of f1 plus f2. So we have from here a lower bound, that this is greater than or equal than 0. Now let's bound from above. So by this equation plus, this is a dot here, we have that this is less than I phi of f1 plus I phi of f2 minus I phi of f1 plus f2. Now each time I apply the equation dot, I get an error of epsilon. So I have 3 epsilon. But now from the lemma, I know that this equation here is less than epsilon. So this is less than 4 epsilon. But here we apply the lemma. Okay, so what we proved that now since epsilon is arbitrary, I is linear. So as epsilon is arbitrary, we get that I is linear. Okay, as I said before, we can put this at the end because therefore I extends linearly to all the continuous compactly supported functions as positive, because it was positive in C+, linear, because we proved that it's linear, so it has a linear extension, and is left invariant, because it was limit of left invariant, functional on C0, C0 compactly supported. And now by Ritz, we get left invariant radon measure. So we constructed at least one Haar measure. So we proved the existence of Haar measures. Now we are going to give now the last proof of this course, that is the uniqueness of Haar measures. Remember, uniqueness is up to a multiplicative factor. So we are going to prove the following theorem. So if G is a locally compact topological group, and we have that mu and nu are left Haar measures, then there exists a constant C such that mu, the first one is the constant times the second one. Okay, so this is the uniqueness of the Haar measures. Okay, let's prove it. Proof. Okay, so we have this mu and nu, and it's going to be enough to prove that for the function that for any f g associates the number integral of f in the nu integral of f in the mu, right? So if we prove that this function is constant, right? So this means that this is equal to this, and therefore these two measures are a multiple of each other, okay? Because they represent the same functional up to this constant. So it's enough to prove that this is constant. So it's independent. Oh, it's constant. Right? Constant. Okay, so we'll take two functions and one f2, and we'll prove that this ratio is the same. Okay. All right. So before that, let's fix V0 in G a compact neighborhood of the identity, which exists because G is assumed locally compact. Maybe I'll write it. Which exists since G is locally compact. Okay, now for any y in this V0 and for any I equal to 1 or 2, we consider the function that to every x associate fxy minus fyx. Okay, this more now if the group were commutative, then this would be just 0. But in general, this is not. It's not a zero function, but this is supported on a set. Let's call it AI. What is this set? This set is so we have to translate on the right the support of f by y, and then we have to translate on the left by y. But then y is chosen in V0, so this is supported in a subset, on a subset of, so it's the support of, this was fi, support of fi times V0 union V0 times support of fi. Okay, and one should notice that AI is a compact set, because one can prove that if you have two compact sets, the product is compact. This comes from the continuity of the product, and now then is the union of two compact sets. So it's a compact set. Now let's use the fact that fi, each of the fi is continuous and compactly supported. And therefore, it is uniformly continuous, which for groups, you write it like this. For any epsilon greater than 0, there exists V, and we can even choose it inside V0, a neighborhood of the identity such that if you take x, any x in G, and you take y, this increment in V, then the difference between xy and yf and yx is less than epsilon. Now let's call this equation with the star. Okay, now so now let f be either of f1 or f2, and okay, for now, yes. Okay, so fix an f. Okay, now pick h in C+, such that, okay, we want to take the support of h inside V, and we want it symmetric. H of x equal h of x minus 1. Why this can be done? And so for this, one might take h of the form rho x plus rho x minus 1. Okay, so choosing this way, one can assume that h is symmetric. It's an even function. Okay, now we are ready for the big first calculation. So then, if I integrate h d nu times f, the integral of f in d mu, I can write it like this. Okay, I can see this as a double integral of, say, h depends on y, f depends on x, d mu integrates in x, and d nu integrates in y. Okay, now let's use the fact that mu is a Haar measure, it's a left Haar measure. So now we're going to multiplicate on the left here by y. So think that y is fixed, right? So we have this integral in x, and now we apply the left translation by y. So what we get the integral of h y f y x d mu x d mu y. Okay, good, like this. Now let's replace the role of nu and mu here. So, and instead the integral of h in d mu integral f in d nu, again this is a double integral, h respect to x f of y d mu x d nu y. What do I do? Now let's again use that that mu is a Haar measure, and what we do, we multiply here by y, or y minus 1. So we have the integral of h y minus 1 x f of y d mu x d nu y. Okay, now let's use the fact that h of x is equal to h of x minus 1, and we have the integral of h x minus 1 y f of y. But now I'm going to swap the order of the integral as well, d nu y d mu x. And now I see this integral first as an integral in y, and now I'm going to multiply on the left by x. Yeah, multiply, and I use the fact that now nu is a Haar measure. So I integrate. Now instead of y, I put xy. So this x minus 1 is going to disappear. So it's h of y f xy d nu y d mu x. Okay, so now we have two similar integrals. Now let's take the difference. Okay, so now let's take the difference of those integrals we calculated. Okay, so we calculated this integral, we bounded this integral, and we bounded this integral. Oh, we wrote differently this integral and this integral. Okay, now we'll take the difference. Let's make precise the quantifier. So thus, okay, so f is going to be one of the fi's, and then eventually there will be the ai, the set we defined before, that contains the support of G. So we get, so that now we will bound this norm. So this is, we wrote it in this following way. So this was the integral. In both cases we had h of y, remember, we had the h of y. And then in case we have f of x, and the other one, in the second case we had f of xy, and the first case f of yx. So now the difference is going to be, so f of yx minus f of xy. D mu, d mu, d mu. Okay, so now this product here is 0 outside the support of h. So we can just integrate only on the integral for y in the support of h. But now on the support of h, we know that so h was inside this set v0, so this function has support in the set a. So this was the integral of now we have x in a. So we have h y f of y x minus f of x y d nu y d nu x. Okay. Now remember that now if y is in the support of v, we was choosing in such a way that this difference was less than epsilon. So this was this equation right here, and plus the fact that support of h was in the function in the set v, we're going to bound this as okay, y in v, so for the first, and then instead of this is just as big as the measure of the set a, h of y is constant in x, and then this other difference is less than epsilon, d nu y without the mu x. Okay, and now this is less or equal than epsilon mu of a integral of all the space of h in d nu. So we have this bound. Good. Okay, so now we divide by the integral of f d nu times integral of h in d mu. No, maybe I should take twice. No, twice nu. Yeah. So I divide by this number, right? So you'll see that now one will cancel this and the other one will cancel this in this difference here. So what I have, so I divide and get, so the integral of f d mu divide the integral of f d nu minus the integral of h d mu divide the integral of h d mu. This is less than epsilon mu of a divided by the integral of f d nu. All right. Now this was for fi. Okay, so I consider the one with I equal 1, and then the one with I equal 2, right? So, and summing, maybe I'll start a new page. We'll have that, okay, the integral of f1 d mu divide the integral of f1 d nu minus the integral of f2 d mu divide the integral of 2 d nu. Remember, this is what we want to prove to be independent on f, right? So we want to prove that this difference is 0. And we're going to prove that this less than every epsilon. So now here I apply the triangle inequality with this value here. And then I will apply twice this inequality. So this is less than the integral of f1 d mu integral f1 d nu minus the integral of h d mu integral of h d nu plus the integral of h d mu integral of h d nu minus the integral of f2 d mu integral of f2 d nu, apply twice the inequality before, have epsilon. So in the first time I have a1 divided by the integral of f1 d nu, and the second I have a mu of a2 integral of f2 d nu. But now, see, this number here is fixed, it's independent of epsilon. So we have that this difference is bound by this number, it's fixed depending only of f1 and f2 for every epsilon. So as epsilon goes to 0, since this is true for every epsilon, we get that this is 0. So hence, the integral of f d mu divided the integral of f d nu is independent on f. And this concludes the proof of the uniqueness up to a positive scalar of the Haar measure. This is the end of the course. Thank you for watching. Bye-bye.